exists. Okay. So for starters, what we are going to do is we are going to look at the what we called as Boussinesq approximation. Okay, I don't know if my spellings are right here, but you can fix that. So if you remember when we started non-dimensionalization, the topic of non-dimensionalization, in that what we were doing was that you have gravity, okay, and you have fluid. Let us say the fluid is between, so in that we did not consider any walls, but let us say the fluid is between the walls, and what we had said was that there are density changes of the order delta rho, okay, and there is gravity. So we had said that okay, the velocity scale is going to be square root of delta rho over rho, and then we had taken a length scale of L across which density changes were delta rho, and we said that the velocity scale is something like this, and then we had said that the pressure scale P naught, let's say, is simply this, and we had derived the equations which were first order equations in this delta rho by rho. Okay, we had derived equations. So equations up to order delta rho over rho. Okay, so we had derived that, let's say this is u star, which is u over this capital U. Okay, and then let's say there is a p star, which is this p over p naught, and we had written this as p bar star plus a p prime star. Okay, and similarly, so I had done this whole derivation for density changes, but I never said why these density changes exist. And then after that we had discussed, okay, what if these density changes are due to temperature changes. Okay, so just focusing on density changes, the equation that we had derived was something like this. We had derived the dimensionless equation plus p prime star plus, so we had also written rho star as rho by rho naught, and this was rho bar star plus a delta rho over rho naught times a rho prime star. Okay, and then the equation that we got was, here we had just another term which represented your buoyancy force, and then we had 1 by Reynolds number del star square u star. Okay, and then the continuity equation was simply, at first order the continuity equation was simply this, u del star dot u star equals 0. And then if these density changes, so if density changes exist due to temperature changes, if these density changes exist due to temperature changes, then how did we write? So if you are looking at full dimensional terms, then we had written that rho minus rho naught was equal to, what was it? Rho minus rho naught was equal to minus alpha T minus T naught, where this alpha is thermal expansion coefficient. Okay, this is just a recap of what we had done when we started doing non-dimensionalization, because these are the equations that we are going to use for Rayleigh-Taylor instability. Okay, so we are going to look at them. We are going to further linearize them in perturbations. Okay, so that's why I'm covering this as of this problem. So if you have this, then for temperature you can make the equation that you have del T star plus u star dot, and then here we had another dimensionless number called the Prandtl number. Okay, this was Prandtl number. So this is this Re is your Reynolds number, and that is simply we had defined it as rho naught u L over mu, where capital U is this. Okay, and then this Prandtl number is simply mu Cp over K, where your K is the thermal conduction coefficient. Okay, K is your thermal conduction coefficient. Okay, you can also write this as mu by rho over K by rho Cp. Okay, and there is some intuition that you can gather from here. Basically, it's a ratio of two diffusivities. Okay, it's a ratio of two diffusivities. If you have any variable, let's say phi in fluid, that is a physical quantity which is diffusing also. Okay, let us say you have any quantity phi that is diffusing. Okay, then we have seen that the units of this diffusivity be irrespective of what phi is. Okay, phi could be anything, concentration, temperature, whatever. This d has to have units of meter square per second. Okay, so this is like a ratio. Prandtl number is like a ratio of momentum diffusivity to temperature diffusivity. Okay, every diffusivity has a units of meter square per second. Okay, so that's what Prandtl number is, and this is what our non-dimensional equations look like. So for the sake of this problem, what I am going to do is I am going to substitute the scales back and convert it into a dimensional form. Okay, because when we are looking at an instability, you will see that we have to non-dimensionalize using a slightly different scales. So substituting the dimensional equation, dimensional variables back, what you will see is that the equation is simply del u by del t plus u dot grad u equals minus grad p prime plus rho rho prime g plus nu del square u, and the continuity equation is simply this, and the temperature equation is del T over del T plus u dot equals, so this K by rho Cp I am going to write it as, let's say, let me write it as capital K or kappa. Okay, and this is what appears here when you dimensionalize the equations again. Okay, for another sake of clarity, what I am going to do is I am going to replace this P prime with pressure and this rho prime with rho. Okay, and the reason why I am doing this is because uh, yeah, I don't have to replace this actually. Okay, I don't have to do any of this, because what I can do is, how was this P bar star obtained? This P bar star was obtained using this rho bar star. Okay, and the equation was that grad of P bar star equals rho bar star times G star. Okay, there's a G star here also, please fix this. So this is the equation that we had. So what I can do is again dimensionalize this. Okay, I can dimensionalize this, and here actually you will get a rho by rho naught. Okay, and what I can do is I can dimensionalize this and add this quantity. Okay, the reason I am adding this quantity is because this is basically 0. Okay, you convert this into dimensional form, you will get grad P bar equals rho bar G, and I'm just adding a 0 on the right hand side. Okay, and the reason why I do this is because then I can write my momentum equation as this. So this is rho prime by rho naught, and here also you will get a rho naught. So let's see. So our rho prime star was defined as rho prime by delta rho. Okay. So when I multiply the equation by rho naught, yeah, you'll get a rho naught here. So the equation that we technically have is minus of grad of p bar plus p prime plus this rho bar plus rho prime over rho naught times g plus nu del square u. Okay, this is the equation that we have. And now what we are going to do is, as we always do in linear stability problems, we have to linearize. Okay, even before linearization, what is the base state? What is the base state of this? What is the base state? So let us look at a problem where you have temperature boundary conditions of something like this. Okay, you are heating the fluid from bottom. You are heating the fluid from bottom. So the density here, you can imagine a density gradient forming, and the density here will be lesser and it will increase gradually as you move up. Okay, and our coordinates are something like this, let's say. So this time I'm going to take a z coordinate here. It doesn't matter, you can take the y also. It's really not. Let's take y for consistency with other problems. Okay, so notice that this is simply pressure and this is simply density. So the base state is when you don't have any velocity. Okay, you do not have any velocity. So when you don't have any velocity, what is the solution that you get? You basically get this equation back. Okay, you get grad p equals rho just give me a second. I think there's a problem. There is a 1 by rho naught here also that comes. Okay, so the equation is something like this that you get. Okay, and then you basically get this equation back. Okay, grad p equals so grad p equals rho g. So what is the pressure at base state? Pressure at base state is, so g is what? Minus g j cap, right? So what is pressure? What is pressure? Minus rho g y plus some constant. Okay, that is your base state. Base state is simply the stationary state where you are saying, okay, I don't have any velocity, okay, and the fluid just exists. The fluid exists in an unstable state, but that is still a stationary solution. Okay, as you have learnt in your schools that this problem is inherently unstable when you have a heavier fluid on top of a lighter fluid. It is unstable, but the solution is a stationary solution. Okay, it's like that inverted pendulum. Yes, in reality you may not observe this inverted pendulum probably ever, but it is a solution of the governing equations. Okay, and the reason why, I mean, you can extrapolate it. The reason why you never observe this kind of a situation in reality is because it's always unstable. Okay, and that is the instability that we are trying to obtain. As you will see, actually it's not always unstable, there are limits to its instability. For small, uh, for some scenarios this may not be unstable at all. Okay, so we have p as this. Now this is our base state. Now instead of writing these as instead of writing these with the subscript 0, the base state solution with subscript 0, I'm going to write it with a bar because we already have that subscript 0 in the scales. Okay, so I don't want to confuse you guys. So let us say this is P bar, and the density is basically actually this is not correct, right? Why is this not correct? Hmm? Why can't I write pressure as simply minus rho g? Why can't I write pressure? Why can I not write pressure as minus rho g by here? Rho is a function of y basically, right? So I can't just integrate it. So instead of doing that, what I will do is I will use this equation, this one, okay, that uh, rho minus rho naught is minus alpha t minus t naught, okay, and then for base state u equals 0, I have to entertain this equation as well. Where did it go? Here. For base state equals 0, you have del square t also equal to 0. So del square t equal to 0, and let's say you have this th and tc, and the distance between them is capital H. Then what is the temperature profile? Temperature profile is what? Let's say this is your y equal to 0. Then temperature profile is what? Th plus Tc minus Th y over capital H. Okay, it's simply the linear profile, right? Steady state conduction solution. This is something that you guys know. So the temperature profile at base state is this. Okay, so if this is your temperature profile, then rho minus rho naught is minus alpha t minus t naught. Okay, so rho is not rho is not a constant. Rho is a function of y. So rho is rho naught minus alpha of this th plus tc minus th over h y minus t naught. Okay, rho is this, and this is what you have to substitute here. Grad p equals rho g, and then find p. So p is basically minus of rho y. So g is constant, dy plus a constant. Okay, so this is what you have to do for evaluating the pressure, and what we are going to denote is that base state. For this problem, we will write base state as base state rho is rho bar, base state p is p bar, and base state t is t bar. Okay, instead of subscript naught, I'm going to put a over bar just to avoid confusion with your scales that we have used. Okay, now notice that in this definition of thermal expansion, I am using some scales. Okay, basically I am using a scale. I am measuring the change in density from some known state. Okay, so if I give you this known state, then from there I am measuring the density changes, because at t naught, at t equals t naught, rho is equal to rho naught. From that rho naught comma t naught point, I am I am considering this straight line with the slope of alpha. Okay, so I know a state of rho naught and t naught. Okay, and this rho naught and t naught, they correspond to the scales that we have to use. Okay, so be careful, don't write rho bar here. Okay, this is not technically rho bar, but you can show that. So if you write, so now let's write the perturbed state. So perturbed state, what do we have in perturbed state? We say, so in your base state you don't have any velocity, so u is simply epsilon u prime. Pressure is this p bar plus epsilon p prime density is this rho bar plus epsilon rho prime, and temperature is this T bar plus epsilon T prime, with an understanding that this epsilon is much less than 1. Okay, we are adding small perturbations to our fields and then seeing how they evolve in time. So let us just look at this thermal expansion equation. We have rho bar minus rho naught plus epsilon rho prime equals minus alpha T bar plus epsilon T prime minus T naught. Okay, this is nothing but rho bar minus rho naught plus epsilon rho prime, and here you have minus alpha T bar minus T naught minus epsilon alpha T prime. Now notice that rho bar minus rho naught is equal to alpha T bar minus T naught. Okay, this is equal to alpha minus alpha T bar minus T naught. That's how we solved for this rho bar. That is how we evaluated this rho bar. So these terms basically cancel out, and from here you get that rho prime is simply minus alpha T prime.
So in that equation, boxed equation base state, that is rho bar.
Where?
The boxed equation.
This one? Yeah, so this is, I was solving for rho u t everything, rho u t p in the base state. Okay, so here I did not introduce any bar, then I started calling base state with bar. This is just solving for the variables assuming no velocity. Okay, assuming no velocity, that's your stationary solution. Okay, today is not a good day for me because I am making a lot of mistakes. So this is defined like this. The thermal expansion equation is not, so what I had written was not a traditional, was not what it's written in traditional way, because this alpha has to have units of 1 by t. So on the left hand side you have 1 by rho naught as well. Okay, so this is what we have. Sorry about this. And then we have, yeah, okay, so please fix this. And then here also again we will have a rho naught multiplying in here. Okay, now things make sense. Please fix this. Okay, there's a, so the thermal expansion equation is defined like this, that you have relative changes in density that are equal to this alpha times change in temperature. Okay. Okay, now once we have this, the perturbed state density, let us substitute this velocity in our momentum equation, and we will retain order epsilon terms only. Okay, so we will ignore any higher order terms. So you have del u prime by del t plus order epsilon square term. So let me write epsilon here also, equals, what do we have? Minus 1 by rho naught grad of p bar plus epsilon p prime, and then we have a plus rho bar plus epsilon rho prime over rho naught, this whole times g plus nu del square u prime. Okay, and there is an epsilon here. Now this is of not use to us because we are doing linear instability. So considering only order epsilon terms, we will have del u prime over del t equals minus grad p bar over rho naught minus epsilon grad p prime over rho naught plus rho bar g over rho naught plus epsilon rho prime g over rho naught plus epsilon nu del square. Oh, hold on. Yeah, I missed epsilon here. Epsilon nu del square u prime. Okay, now notice again this one. okay, these two. So you have minus grad p bar plus rho bar g over rho naught. Okay, we have defined p bar, that is the base state pressure, using this equation. I mean, we obtained it. Okay, when we substituted u equals 0, we just obtained that grad of p bar equals rho bar g. So these terms basically cancel out. Okay, and then everything else that remains has an epsilon in front of it. Okay, so removing that epsilon, we get the linearized perturbation equation as okay. We get the linearized perturbation equation, and we can substitute for this rho prime using this. So rho prime over rho naught is just minus alpha t prime. So this is minus grad p prime over rho naught, and then a minus alpha t prime plus nu del square. Okay, this is our simplified linearized momentum equation. And now we substitute the same thing in temperature, and what do we get? Del T prime over del T plus, so this will be epsilon del T prime over del T plus epsilon u prime dot grad of T bar plus epsilon T prime. I just omitted the T bar term here because I know that's not varying in time. I just omitted it directly. By now, most of you should have gotten the drill of what's going on when we do the linearization. Basically, whatever terms we see are quadratic, we have to simplify those. Whatever terms are linear, they just linear. Okay, there's nothing fancy going on here. Yeah.
So how did we get that alpha t dash in the time step?
I just there's a G also, if that's what you meant. Okay, so when you do the linearization, order epsilon square terms can only appear from quadratic or higher order terms. So the idea is to just drop those higher order terms altogether. Okay, so the straightforward linearization step here basically yields this. You have u prime dot grad t bar equals k del square t prime, because del square t bar was 0. That's how we evaluated the state, base state. Okay, remember all the solutions here we are putting a subscript bar for them. The base state solutions we are putting a bar over them. And now this equation also we can further simplify. If I write this u prime bar or u prime vector as u prime v prime w prime, then I know that grad of t bar only exists in y direction. This is your t bar. Okay, grad of t bar only exists in y direction. So this will be effectively and dt by dy is simply v prime tc minus th over h equals Okay. So, what I am going to do is I am going to define this Tc minus Th as, so what I am going to write for this is that, so I want to write Th minus Tc as delta T. Okay. I want to write this Th minus Tc as delta T. So, temperature is decreasing. So, I can replace this term with a minus of V prime delta T over H. Okay. That is the equation that I will get. So, now we have a system of linearized PDEs. Okay. We have a system of linearized PDEs, and of course, there is del dot u prime equals 0. Let us not forget about it. So, we have a system of linearized PDEs. Now, as in any instability problem, what do we do now? We have to identify the, what do we have to do? What is the next step? Once you have linearized PDEs, to convert them into linearized ODEs, we have to identify the homogeneous directions. Which are the homogeneous directions in this problem? Just x, x and z. Okay. Your solution is homogeneous, base state solution is homogeneous in x and z, and technically the problem doesn't depend on how much you extend these plates. If you're not going to consider any boundaries in x direction and z direction, then this could be anything. Okay. So, we will do the normal mode assumption basically that we have been talking about. Before we do the normal mode assumption, I want to introduce a different type of non-dimensionalization for this problem, which is again a very standard non-dimensionalization that is done. Okay. And the non-dimensionalization goes something like this. So, the scale for t prime I am going to choose as delta of t. Okay. The scale for x, y, z I am going to choose as this capital H. And now comes the tricky part of y. I am choosing a scale of time using this h square over kappa. Okay. And then the velocities I am choosing a velocity scale of kappa over h. Okay. And pressure scale is just P prime is just P naught. Okay, which we will pick as rho naught. So, this is your u naught, and we will choose rho naught u naught square. Okay. Now, for a moment let's think about this time scale. What does this time scale represent? This kappa k is your thermal diffusivity. This kappa k is thermal diffusivity. So, what does this time scale represent? This h square by k term. Hmm? What does this h square by k term represent? Huh? That's time scale of temperature diffusion over a length h. Okay, time scale of temperature diffusion over a length h. Basically, how long will it take? So, for example, this state Tc and Th I have established by heating the bottom plate somehow, and then let's say there is some temperature perturbation that exists here. Okay, in this local region the temperature suddenly becomes slightly higher than this, whatever the variation you will get from the base state profile. How long will it take for this temperature to diffuse over a length scale of capital H? That's what that time is, that time scale is representing. Okay, it's a time scale of diffusion. Okay, so it's like telling you, okay, if you want to measure this diffusion process, then this is what you have to consider. Now, why is that important? There are other time scales also that we can formulate. Okay, we could have formulated a time scale based on momentum also. I could have, instead of h square by k, I could have written h square by nu. That is also a time scale. I could have written h square by nu, that is also time scale. I could have formulated a velocity scale based on the temperature scales like we have done with buoyancy. Okay, if you go back, like we have done with buoyancy, I could have formulated a velocity scale using that, and then using h and velocity scale, I could have formulated a time scale. Each of them mean different things. If you define it using momentum diffusivity, then instead of temperature, you are saying, oh, there is some velocity perturbation, how long it takes to diffuse this velocity perturbation. And there is no reason why that time scale should be equal to this time scale, because it all depends on this new parameter instead of this kappa parameter. And the other one, if you define a velocity scale and using that you define a time scale, what does that represent? That represents, okay, how long, if there is a blob of some velocity, how long does it take for this blob to convect itself upwards at a distance of capital H? Diffusion, convection, they are completely different processes. So that time scale is again physically very different from this time scale and the h square by nu time scale. Okay, we are picking this time scale. We are picking this time scale. Now, this is not a very thorough reasoning. This is a very hand wavy reasoning, and the reasoning goes something like this: that the reason I am picking this time scale is because I expect that if my temperature perturbations diffuse out very quickly, if my temperature perturbations diffuse out very quickly, then I am not going to have any instability, because before those temperature perturbations can cause, due to buoyancy, some finite velocity, there will be nothing that will happen, because in that time temperature diffusion will take over and diffuse out the inhomogeneities. And that is the reason why I am picking this. Basically, I am pinning the reason for this instability to be temperature diffusion. I am saying that because there is temperature diffusion, or because there is not sufficient temperature diffusion, this instability happens. That is what I am saying, okay, by doing this. Okay. Again, that is not a very thorough reasoning, because I could pick h square by nu and carry on with the analysis, and you will get similar results. It is just that one non-dimensional parameter that you will get differently. Okay. Now, putting these in your perturbation equations, so let us put here. So, I will have a u prime star as u prime over that u naught. Okay, and then I will have a p prime star as p prime over this p naught, and then a t prime star as t prime over a t naught. So, the temperature scale that I am going to pick is the temperature not t naught, sorry, delta t. That is what I have written here. Okay. So, now substituting them here, now time and length scales I am assuming that you guys are comfortable about here. So, you will simply get a u naught over this h square by k times del u prime star over del t star minus, what will you get here, 1 by h, and then a p prime has p naught, and then you have a rho naught, okay, grad star of p prime star plus a rho prime, but oh, instead of rho prime we are working with t prime, right? So, minus of alpha t prime star g and then a delta t plus nu and then a u naught by h square del star square u prime star. Now, p naught is rho naught u square, okay. So, this guy is rho naught u square, and then we have it's minus u naught square h square over kappa u naught h delta t h square alpha over kappa u naught, and then a t prime star g vector plus, what do we get here, nu u naught over h square times h square over kappa u naught del star square u prime star. Okay, and now, so u naught, this cancels out, this cancels out. Okay, and what I'm going to do here is, so here you will see that there's a nu by kappa that remains, everything else cancels out. So I'm going to now multiply the whole equation by kappa by nu. So I'm going to write it as kappa over nu del u prime star over del t star equals, so here what do? We get a h by kappa, right? Did I miss anything else? Yeah, minus u naught h over kappa, and then I'm going to multiply by this del star p prime star. And now when I multiply here by kappa by nu, we'll get a very recognized number in these kind of problems, which are called natural convection problems basically. Okay, so you have u naught h by nu. Okay, yeah, u naught h by nu, which is nothing but kappa by nu. Okay, u naught h by nu is kappa by nu. So you have kappa by nu del u prime star over del t star equals minus kappa by nu del star p prime star minus, so now look at this term, alpha delta t over, let's substitute for u naught, nu kappa, and then an h cube t prime g plus, and now this number that you see here, basically this is called the Rayleigh's number, and the definition is that alpha delta t times g times h cube over nu kappa. That's how Rayleigh's number is defined in these natural convection problems. Okay, basically you can look at this, problem, you can look at the Rayleigh's number as a product of two non-dimensional numbers. Okay, I will leave that mathematical manipulation to you guys, that one, you can get it as buoyancy over buoyancy force divided by a shear stress that you will get, or shear stress or any viscous stress, let us not call it shear only, buoyancy over viscous stresses. So buoyancy force over viscous force, you can write it like that. Okay, and then you will also have to write it like buoyancy force over viscous force times the viscous over thermal conduction time scales. Okay, so you can look at this Rayleigh number as a product of two dimensionless numbers. Okay, and I hope whenever you have covered natural convection problems in heat transfer, you have looked at it before. Yeah, you can call it a lot of things. I can call Grashof as Rayleigh by Prandtl also, right? So there's Rayleigh, but yeah, you're right in that terms. So others, you have seen this Rayleigh number in natural convection problems, huh? So this Rayleigh number appears here, and then what we can do is this nu by k is, so this k by nu is 1 by Prandtl number, and then I can multiply the whole equation again by nu by k. and I will get del u star equals minus and then a minus of Rayleigh number. So notice there is a g here, that is acceleration due to gravity, and this is g vector. Okay, so technically this term that you see here is Rayleigh by g. Okay, so Rayleigh by g and then a t prime star. There should be a star here. T prime star plus a. So we are multiplying with nu by k. So there is a nu by k. So Prandtl number also appears here, and then a Prandtl number del star square u prime star. And this is the final dimensionless linearized momentum equation that we get. So noticing that your g vector is just minus of g j cap, okay, minus of g j cap, that is what your, so I can write the y direction momentum equation as simply like this. Okay, it is easier to write that. Plus Prandtl number into Rayleigh number t prime star plus Prandtl number del star square v prime star. Okay, for u prime and w prime you just won't have this buoyancy term, which makes sense. Also the buoyancy forces are only in y direction because gravity is only in y direction. Okay, so let me just write them quickly. So you have u prime star p prime. Okay, p prime star. So there is no buoyancy term here, plus Prandtl number, and then we have a z direction velocity perturbation equation. Okay, these are our dimensionless linearized momentum equations. What is our dimensionless continuity equation? Simply this. So we have okay, the continuity equation is simply this, and now we have to look at the temperature equation. Have I okay, I haven't even started. Yeah, here. So now we have to look at the temperature equation. So let us quickly non-dimensionalize our temperature equation also. So we have a time scale of h square by k, and then temperature perturbations have a scale of delta t. So we will have delta t k, kappa or k whatever h square del t prime star over del t star, and then a minus of u naught v prime star. Here you already have this delta t over h. Okay, equals kappa over h square delta t, and then a del square of t prime star or del star square. Okay, delta t k delta t kappa over h square is common in these terms. U naught is what? Kappa over h. Okay, u naught is kappa over h. So that will also cancel because you will have kappa delta t by h square in front of all three terms, and your dimensionless equation will be okay. So now we have a system of dimensionless linearized equations. We have dimensionless momentum equation, we have dimensionless continuity, and we have dimensionless temperature equations. Okay, and in our next class we will look at how to substitute normal mode assumption here.